Hello, I'm Chad Gibbons, and this is my final project report for Georgia Tech's CS8802 Advanced AI for Robotics. For my final project, I have built a small robot platform, and I will have it perform localization in the small world that I built here in my home gym. The robot is using an augmented Monte Carlo localization algorithm using particle filters. The world is a replica of the one-dimensional hallway example frequently used in the probabilistic robotics text. I use wooden blocks to simulate the hallway and gaps in those blocks to simulate the doors. The robot has an ultrasonic sensor to detect the distance to any obstacles. In this world, the wall is approximately 50 centimeters away from the robot, while the gaps provide a measurement of 120 centimeters, reflecting off the wall behind the wall, the wooden block wall that I've made. My goal for the little robot is to attempt to localize itself and find the third door. If it does, it'll do a little dance and let us know that it's made it there. Let's see it in action.
So in this first test, I started the robot at the very beginning of the robot world. You can see it marching slowly forward, pauses after each motion and takes a sensor reading, and I did that just to make it easier for me to debug. As you can see from the measurements, they correlate exactly with the walls and the gaps. And here we go. It should find, and does, the final hole where it thinks the third door is, and does a little dance. Now in the second test, I actually started the robot at the first door. In this case, localization really does have to work because it can't just guess from the map where that third door is. So you actually see the estimates start to correlate more and more rapidly to where that final door is, and there we go. Does a little dance. Okay, now that we've seen the robot in action, let's actually talk about the hardware platform that I used, some of the trials and tribulations of what I ran into, and you'll notice I've got two robot chassis here, so I'll talk about that little experiment in a moment as well. This is the chassis that I used in the experiment. This is a two-wheel drive robot chassis originally purchased from Make Magazine, and you can see it has an Arduino with a Adafruit motor shield on it. Real simple robot platform. Works pretty fantastically. I've had this for a year and a half or so and just used it to do some basic experiments before I really knew anything about robotics. This thing also has an ultrasonic sensor that's good up until about 175 centimeters. That's pretty good range. And it's mounted on a servo, which is very useful. And as you saw in the experiment, I only used it at 180 degrees because I was really only concerned with one-dimensional map. This thing has, I think, 5 AA cells that are rechargeable that I use, 2 motors, and that's really it. It has a standard caster for steering, or keeping the robot from tipping over. What I did extra to this robot, and I discussed this in my abstract, was I wanted to run a real computer that could run Python and have it control the Arduino. The Arduino is 8-bit, and even after the motor controller libraries were installed, I only had about 30 kilobytes of program space left over, and I knew that would not be enough to do the kind of localization I wanted to do without a lot of fixed point magic and stuff like that. And while I'm sure I could do it, I didn't think it was a good use of my time. So I knew I had Raspberry Pis, and I knew they'd be easy to use. So I went ahead and went about hooking these up. And the way they actually are hooked up is, this is an I2C connection that I did. And luckily, just out of coincidence, the way the Raspberry Pi is configured, it has internal pull-up resistors, so I can do a direct connection without any issues, even though this is a 5-volt board and this is a 3.3-volt board. It all just works out. It is possible to power the Raspberry Pi from the Arduino through one of the input pins, but that's a little risky. There's no protection circuitry. So instead what I did was had this external USB battery and just had the Raspberry Pi connected directly to it. Works out great. I ran this thing for hours at a time without a problem with voltage whatsoever. So the interesting thing that I ran into, and you probably saw some of this in the demo, was this robot chassis does not track straight. It's pretty good, but sometimes randomly it just goes off in one direction or the other, and watching the wheels, you can see certainly that these things wobble, and on fairly low-end robots I have come to learn that that's fairly common. I did not get a chance to do wheel encoder tracking, which is what this kit was for, and I just never got time to do it. So I wasn't able to do proper PID control and actually adjust the cross-track error and all that based on input. So I had to guess and use trial and error. And what I was effectively doing in that demo was turning the robot to the right 1 degree after every forward motion. It worked well most of the time, but not 100% of the time. So this experiment worked out great. The code to control the Arduino from the Raspberry Pi is trivial. It's just a few simple ITC bus commands. And the Arduino code itself is trivial as well. And while I know we don't have to discuss the code and provide the code as part of the project, I am going to link to it in my final report so you can see what was involved here. I did have a lot of issues with getting this to work consistently, and it was a very interesting experiment. The probabilistic robotics text was very useful in this. I had to do an augmented Monte Carlo to get everything to work out correctly. In the end, things began to be very predictable, so I'm really happy with how this turned out, and this was a lot more fun, and I wish I had more time to do more of what I had originally planned. I'll go into that in more detail in my paper. Wanted to talk about this real quickly. So this came out actually after I had written the abstract, and I wish I could have been able to use it because I think it would have been more elegant. So this is a Magician chassis, which is literally $15. A Raspberry Pi, and then a Raspberry Pi based motor controller called Raspy Robot. I'm going to go ahead and take it off. And very simple motor controller. Worked great, you know, and then actually the guy that designed it was smart enough to think about input power, since that's a problem for Raspberry Pi. So you can actually power the board through a standard barrel connector here, and everything works great, with one exception. Version 1 of this board did not do pulse width modulation to the motors. It was on or off. And as you probably have already figured out, you combine that with no wheel encoders, and you have a robot that does not drive straight at all. In fact, this one was so bad, the best I could get it would be about a 4-to-1 turn to straight ratio. It was pretty horrendous, so I gave up using that. It turns out he has a version 2 of the board that had all the features I wanted, but I didn't have enough time to order it and or make my own. So that was unfortunate, because just from a cleanliness perspective, you could certainly see how that would be a little bit more fun to work with. So overall, really super fun project. I enjoyed the hardware part of it. I always do, even though I'm bad at hardware. Soldering is always amusing, but it is great fun to be able to build stuff and see it in action. And, you know, frankly, one of the best parts about this class was being able to take all this great stuff we learned about software and actually apply it to real hardware and see it in action. And so much more about what we were taught clicked in that procedure. So I wanted to thank you much for watching, and really enjoyed the class, and I hope I get to work with this stuff more in some future classes. Thank you very much.